Okay, so quick explanation of why mist, which are tiny little particles of water, why mist falls slower than rain. Okay, well, the main difference between these two is obviously the diameter, the size of them, the radius of them in particular. So what we're going to do is we're going to look at the radius. Now they're both made of water, they both fall through air, and it's going to come down to, if we think about our free body force diagram for one of these, we're going to have the weight acting downwards, we're going to have up thrust acting upwards, plus the viscous drag. Okay, so we assume both these two fall down. So here's our free body force diagram for these. Let's just check out what's going to happen at terminal velocity. And at terminal velocity, we know that weight is going to be equal to up thrust plus drag. Okay, now the weight and the up thrust, well, the up thrust is going to be negligible. So let's assume U is negligible. We can probably make that assumption because the air, in terms of density, the air is so much less than water. So therefore, U equals 0. That's the assumption we're making, and we could do this without making that assumption, but it'll just help a little bit. Now we know Stokes' law. We already know is D is equal to 6 pi r eta v, and in this case we're looking at terminal velocity. So what we're saying is W equals 0 plus D. So we're looking at D, so 6 pi r eta Vt is equal to the weight, which is equal to mg. Now I've got R over here. Now R obviously actually features over this side as well, because it has something to do with how much mass there is. So another formula we know that we're going to have to use, we know that mass is equal to density times volume, and we know that volume in this case, I'm being careful here to keep this looking like a capital V rather than a little v, we know that volume is equal to 4/3 pi r cubed for a sphere. So I've got mass is equal to that. So I'm just going to change colour pens because it's not particularly clear. So on the left hand side over here are formulas that I'm going to use. I'm going to substitute into this. And ultimately what I'm trying to do is find Vt. Okay, so I'm going to keep Stokes' law on the left hand side for now. So 6 pi r eta Vt is going to be equal to the mass. Well, the mass now is this horrible looking thing over here, density, and this is density of the water, 4/3 pi r cubed g. Now what I'm going to do is I'm going to just isolate Vt on its own. So I'm going to move everything across. So I'm going to put 4/3 over here for a moment. 4/3 rho pi r cubed g, and then pop everything else under this. So I've got 6 pi r eta. Again, that's it, and the Vt stays over there. Right. What have I got? This pen's starting to bleed a little bit, sorry. On the top now I'm going to have 4 rho, the pi's cancel, one of the r's cancel, so r squared g. So one of those r's cancels there. All over, I'll delete 3 times the 8 gives me 1624 eta. Now for the water, so that was the terminal velocity. That's the formula for the terminal velocity of these. If I go back over here now and consider these 2 droplets of water, well, the only difference between them, and I'm going to change to another colour now again to see if this colour works a little bit better. The only difference is R. So I know that the terminal velocity Vt is equal to 4/24. Well, that's the same as if I divide by 4. Wait a minute, I don't think this is right, is it? 4/24. I'll leave that for now. There might be a mistake there. 4/24. I don't think it's a 6. I think it's 2 9s. Anyway, 4/24. In fact, you know what? I'm going to leave that because I don't trust that one. All I know is Vt is proportional to all these. The density of water is the same, G is the same, the viscosity of the air is the same. The only difference is it's proportional to that. So what that tells me is this: as R goes down, the terminal velocity goes down. Well, R here is very, very small. and R here is much, much bigger. Therefore, V the terminal velocity will be much bigger, and this terminal velocity will be much smaller, which means it will fall much slower. Okay, now I'm off to check the maths over here. Okay, I found a mistake. My pen bled here. This looks like an 8 when I read it. It actually says a 6, which means this isn't 24. This is actually 18, which means over here the final formula would be, if 4 over 18 is 2 over 9, so 2 over 9 density R squared G all over eta. Now obviously this would be slightly different if I wasn't going to make that assumption there. So in reality, if we assume upthrust as well, acting upwards, that's obviously going to slow this thing down even more because it's going to add an extra force upwards. So whatever I calculate the terminal velocity to be will be a slight overestimate, okay, because I've assumed there's no upthrust when in fact there is a tiny amount.